A very good morning to all of you. Today we are moving to week 4, part 3 topics. We will discuss uninformed search techniques, greedy best first search, and A-star algorithm. So first we will discuss greedy best first search. If you are using a Google map, it shows the road that actually looks closest to our destination. So not necessary that path will be the cheapest or shortest in total distance. That means the app chooses what seems best right now. So it does not look at the full cost so far. So this we can consider it as the greedy behavior. This is exactly how greedy buzz for search works. So here, greedy buzz for search it evaluates the node by using heuristic function, that is mm, h of n. So h of n is the heuristic function that estimates the distance to the goal. So here we can say that here f of n is equal to h of n. So that means no path cost will be considered. That is g of n. G of n is the path cost from one node to the next node. So no path cost is considered in the greedy buzz for search. So it only choose closeness to goal matters actually here. So we can say that greedy buzz for search expands the node with the lowest heuristic value, that is h of n, and that is the node that appears closest to the goal. So here we can say that here it will consider only h of n. H of n means the node that appears to be closest to the goal state. So it shows the greedy behavior. Here we will see the map of Romania. So here we will explain greedy buzzword search using this picture. The picture shows the cities of Romania. So here we are considering our initial state as Arad. So that means starting point is Arad and our goal state or the destination is Bucharest. And here the state space is cities on the Romania map. And the edges means the roads with the distances. That means here we can see the road from one city to another with the kilometer. The distance is also mentioned here. This is the edge. And the heuristics. Here we can see a separate table. So this is the heuristics we are using. Heuristics means h of n. Here the heuristics is straight line distance, that is HSLD. Here it is given that HSLD. So that is a straight line distance to Bucharest. So that means if Arad, it is given that Arad is 366. That means from Arad to Bucharest, the straight line distance is 366. For example, you can see FORE 161. So that means from FORE to Bucharest, it is 161. So here we will see how the greedy bus works. So here we are more, our problem is find a path from Arad to Bucharest using greedy bus search. And here the heuristic used is h of n is equal to h of SLD, that is straight line distance from city N to Bucharest. And the evaluation function is f of n is equal to h of n. So here our evaluation function is f of n is equal to h of n. H of n is the straight line distance from the city N to the Bucharest. And here we can see our starting node is Arad. So Arad to Bucharest, actually the straight line distance is 366. It is given. We are expanding that node Arad. So Arad, you can see that there are three child nodes are there. You can see from Arad we can go to Serint, we can go to Sibiu, and we can go to Timisoara. So these are the neighbors of Arad. And here we can see, we can consider from Serint to Bucharest. So h of n of Serint is 367. Serint is 367. And from Sibiu, for Sibiu, you can in the table you can see from Sibiu to Bucharest, the straight line distance is 253. And then next neighbor is Timisoara. From Timisoara to Bucharest, it is 329. So we are considering these three h of n. So which one is the lowest? And here you can see the greedy buzzword search selects
the lowest one h of n, that means it will select CPU. So it will select, next it will select CPU. We can see in the next slide. Here we can see there are three neighbors, and the three neighbors from Sibiu to h of n is 253, and Timisoara to Bucharest the straight line distance is 329, and Serin to Bucharest the straight line distance is 347. So it will select Sibiu because this is lowest. Then from Sibiu we will consider its neighbors. So Sibiu, there are four neighbors are there. Arad. Arad to Bucharest is 366. The next is actually Fagras. Fagras to Bucharest is 176. Then next is Oradia. Its h of n is 380. And next is Riminicu Vilcia. It is 193. So here 176 is lower. So from Fagaras to Bucharest, it is only 176. So it will select the Fagaras. Then from Fagaras is selected. That is the lowest heuristics. So then that means here we are not expanding these nodes because the lowest edge of n is selected and we will expand the further nodes. So greedy best first search always follows the node closest to the goal. Then next Fagaras. Then Fagaras, there are two neighbors are there, Sibiu and Bucharest. Sibiu to Bucharest is 253 and Bucharest to Bucharest it is 0. So it will be selected. So we got the path. Our path is from Arad, from Arad to Sibiu, Arad to Sibiu, then Sibiu to Fagras, then Fagras to Bucharest. So this is the path. So figure shows the progress of the greedy bus first search using HSLD to find a path from Arad to Bucharest. So here the greedy bus first search using HSLD to find a solution without ever expanding a node that is not on the solution path. So here, so this is the path here, and although the path Arad, Sibiu, Fagaras, Bucharest. So this is the path we got. Arad, Sibiu, then Fagaras, then Bucharest. So although it reaches the goal quickly, the path selected via Sibiu, Fagaras, Bucharest is 32 miles longer than the shortest path through Riminicu, Vilesia, Pitești and Bucharest. Here we can see that actual distance, actually we have to travel here 140 plus 99 plus 211 kilometers. But if you are choosing this path, Arad to Rimnicu Vilesia, then to Pitești, then to Bucharest. If you are selecting this path, then you can see its distance is actually from 140 plus 140, then 80, then you can see here 80 to 97 plus 101. So if you are choosing this path, this is actually 132 miles lower. So this happens because the algorithm considers only the heuristic value h of n, which estimates only how close a node is to the goal and ignores the actual path cost. So for this reason, this algorithm is called a greedy at each iteration. It chooses the node that appears closest to the goal node at that moment. However, this greediness can cause the algorithm to miss the optimal solution that will leading to worst result. So that's why we are moving to the next algorithm, that is A star algorithm. So the main problem is we are considering only h of n. So that means we are actually choosing the closest path, which node that appears closest to the goal at that particular moment, and it ignores the actual path cost. Then next we will see the properties of a greedy bus first search. So we know that greedy bus first search select the node that appears closest to the goal using a heuristic function. So we know that h of n, f of n is equal to h of n, where h of n is the estimated distance from node n to the goal state. And here we are not considering the path cost, and the decision is local and greedy. And greedy best first search may give a longer path, so we can say that it does not guarantee the optimal solution. And the next point is actually if we are considering a finite state space, that means if there are 10 rooms and we are searching a key and key in the one room, then we will eventually find it. So that means it is finite space means it is complete. And for infinite state space, if the room keep appearing forever and you always choose the room that looks closest to the exist. So that means you may never stop, and so it is not complete. So that means we can say that creative first search is complete in the case of finite space and it is not complete in infinite space. Then we will see the time and space complexity. So if you are considering B as the branching factor and M is the maximum depth, then it stores many nodes in the memory. So that means it requires high storage space. So here we can consider the space complexity is actually big O of B to the power M. But with the good heuristics, it can be reduced to big O of B into M. Next, we will see A star algorithm. So we want the shortest path from a start node to the goal. So like Google Map find the shortest route. So moving from one place to another has a cost. So that means distance, time, or it can be the effort. So sometimes we can guess how far we are from the goal. So that means A star uses this guess to decide which path looks promising. So for example, we can say that imagine we are walking in a city and to reach a coffee shop. So we know that the distance you have walked is g of n, and we can estimate how far it is from our current location to the shop, that we can take it as h of n. So then, so in that case, here the evaluation function, that is f of n is equal to, f of n will be equal to h of n plus g of n. So we are considering h of n and g of n. So g of n is cost from start to current node. That means how much you have traveled so far. That is g of n. And then that means from the start node to the corresponding node. The h of n is estimated cost from the current node to the goal state. Your guess of remaining distance. So we can write f of n is equal to g of n plus h of n. That means total estimated cost will be sum of the distance traveled plus estimated distance remaining. So here we can see it is written the equation f of n is equal to g of n plus h of n, and f of n is the estimated cost of the cheapest solution. G of n is the cost to reach the node n from the starting node, and h of n is the cost to reach from the node n to the goal state. So greedy bus first search that actually uses only h of n. So only look at the goal, may ignore the path already taken, can be short-sighted there. But in the case of A star, that combines both, considers both the path so far and also what remains, that is smart and efficient one.
Here we will see the same example. We can see the cities on the Romania map. Here each node represents cities and edge means the actual road distance. Then and the goal is Bucharest. And here we want to travel from Arad to Bucharest. And here we can see the heuristic table is also given on the right side. And here that is a straight line distance, that is HSLD. And this is our heuristics H of n that gives an estimate of how far each city is from the goal state, that is from Bucharest. So here we have to consider, in the case of A star algorithm, we have to consider G of n, G of n, and then H of n for calculating F of n. And H of n is given in the this table. That is on the right side you can see straight line distance. That is H of n. And G of n we can calculate from the picture. So for example, we can say that G of Sibiu. G of Sibiu means from start node to Sibiu, what will be the cost? So that means G of n will be equal, here G of n will be equal to 140. So from the start node, that is Arad to Sibiu, what will be the cost? So here, the case of Sibiu, G of n will be 140, this distance. And so then H of CPU, we can see that it is in this table, we can see H of CPU, that is 253. So we can calculate F of n. F of n is equal to 140 plus 140 plus this 253. So here the F of n will be the sum of this H of n and G of n. So it will be equal to 393. So here we have to do this similar operation for Timisoara and Serent. Here we can see that from Arath there are three neighbors, Sibiu, Timisoara and Serent. So we have calculated f of n for Sibiu, that is it's g of n plus h of n. And similar to that for Timisoara also we have to take g of n and h of n. So that means here we have Timisoara 118 is the G of n. So that means from Arad to Timisoara 118 is the distance, and then from Timisoara to Bucharest the HSL straight line distance is 329. So we are calculating it as 447, and for Serent also we will calculate G of n and H of n. Then so that means we expanded Arad. There is the start node and we are considering all the neighbors and calculate G of n plus H of n, that is F of n for each node, and the and the Timisoara, Sibiu and Serent, and we can see that here Sibiu has the lowest. So here the CPU has the lowest f of n. You can see it is only 393 when compared to other two neighbors. So we will expand the next from CPU. Some CPU there are four neighbors are there. That is Fagras, then Arad, Fagras, Oradia, and then we have Remnicu Vilcia. So here for each one we will calculate f of n. Then you can see its value from Arad we are calculating g of n plus h of n, and Fagras we are calculating g of n plus h of n. Next city, next city. For each city we are calculating f of n, g of n plus h of n, that is f of n. Then from this here we can see that this one we already expanded the Arad. Then next we are comparing all this. We know that here the lowest one is actually Remnicu Vilcia. So that means Reminique Villicia is now has the lowest, that means 413, that is f of n. So, so it will be expanded next. So not that actually the nodes already expanded like Arad, we will ignore it. Then here we can see we are expanding the Remnicia Vilcia. So there we can see that there are three neighbors, Sibiu, Pitesti and Craiova. So here also we will find g of n plus f h of n. Then here we can see these three neighbors. Which one is the lowest? F of n. So this is actually Pitesti. Pitesti has the lowest value. It is only 470. So here the algorithm is moving towards the most promising path, balancing h of n and g of n. Then you can see that from this Pitesti again we are actually expanding. So from now we can see that here we are next expanding Pitesti. So Pitesti, there are three neighbors are there, that is Bucharest, Craiova and the last one is Rhyminica vilcia. So here you can see that Bucharest has the lowest value. Here you can see it is a 418 compared to other. This has the lowest f of n. So A star reaches the goal node. So the optimal path from Arad to Bucharest is found, and the path cost is 418 miles. Now we will see this is our path, Arad to Sibiu, to Rymnica Milicia, and then Vitesti, then to Bucharest. Next, we can see another example. Here we can see a graph with the nodes S, A, B, C, D, G, and here and also the edge is labeled by the cost, and a heuristic table is given. You can see here h of n, that is estimated cost from node n to goal state. So that means here from the starting node S to goal state it is 5, A to goal state it is 3, like that. And then here we have to calculate f of n. We know that in the case of A star algorithm, the formula of f of n is g of n plus h of n. G of n is the cost to reach any node from the start node, and h of n it is given in the table. And g of n we have to calculate it from the figure. So initially we are starting from S. Here our start state is S. From S, we are calculating f of n. So f of n, we know that g of n plus h of n. So here, in the case of S, we can say that g of n. Then that means from start node to this node. So that will be, anyway it is 0 because this is a start node. Then h of n. Then the start node to goal state, h of n. So that it is given in the previous table. We have already seen the table. So from that we know that h of s, h of s is it is given in the table, that is actually 5. So it is 0 plus 5. So f of n will be equal to 5. It we are writing here. Then next iteration, yes, we have two child nodes A and G. We will first see for A. For A, G of n is from starting node to A, that is 1. So 1 is the G of n. So 1 plus then h of n. H of n is from the table we have to take h of A to the goal state. What will be the distance? From A to the goal state, that is h of A is equal to 3, then 1 plus 3, that is 4. So it is written S to A, it is 4. Then similar to that, S to G. S to G also we know that here S to G means here G of n is 10 and H of n from goal state to goal state, anyway it will be 0. From the table also we can understand it is 0. So it will be S to G is 10. When comparing these two, this is less. So we are expanding A. Node A has two neighbors. Here you can see it has B and C. When we are considering B, so B, G of n. G of n means starting node to B. So starting node to A is 1. Then A to B is 2. So total there is 1 plus 2, that is 3. So G of n will be start from the cost from starting node to node B. So then S to A is 1, A to B is 2. So total G of n will be 1 plus 2, that is 3. Then H of B. H of B is given in the table. In the previous slide, we have already seen the table. So we know that H of B is actually 4. So there is 3 plus 4, that is 7. So here SAB is 7. Then if you are going to C, that means A to C, then the G of n will be starting node. S to A it is 1, A to C it is 1. So 1 plus 1, 2. So it will be 2 plus then H of C. From the previous slide, in the table we will get H of C, that is equal to 2. So it will be S to A to C it is 4. So lowest is this one. So that one will be expanded. So here C will be expanded. C has two neighbors D and G. Then we will see first D. So D, first we will calculate G of n. So starting node, we will start from the starting node. S to A is 1. A to C is 1. So now it is 1 plus 1, 2. Then 2 plus D, that is 3. So 2 plus 3 will be 5. So here G of n will be 5. Then 5 plus and H of D. H of D is actually we have to take it from the previous slide table. Their h of d is given as 6. So it will be 5 plus 6, that is 11. You can see here S2ACD is 11. And then we can see G. If you are opening G, then it will be G of n will be starting node. S to A 1, A to C it is 1. Now 1 plus 1 2, and C to G it is 4. So 2 plus 4 6. So it will be 6. Then gold state to that is this is the gold state to gold state. It is from the table we know the h of n is 0, so it will be 6. So S A C G, that is 6. So now we reach the gold state and our optimal path is S to A to C, then to G with the total cost 6. So the iteration 4 will give you the final result, that is S to A to C, A to C to G. It provides the optimal path with the cost 6.
Here we can see another example. Here we have the start node S and the goal state is G. And here the cost from one node to next node, it is actually specified here. You can see S to A it is 3, S to D it is 4, like that. And then the h of n, it is for S to gold state, h of n will be 11.5. From B to gold state is 5.8. From gold state to gold state it is 0. So along with each node, h of n is given, and g of n, that is the cost. Cost from one node to next node is given along on the edges. Here we can see the solution. We are starting from this node, starting node S. Yes, we have two neighbors, that is A and B. Here you can see A and B is there. So we will calculate the f of n. For A, it is g of n plus h of n. So that means from start node to A, g of n is 3 and h of n is 10.1. So it will be 13.1. Then if we are going to node D, then you can see here from the first figure, you can see from start node to D, the cost is actually 4 and h of B will be 9.2. So if you are adding 9.2 plus 4, that is 13.2. So then if you are checking these two, we know that this is the lowest. 13.1 is the lowest. So now what we will do is we are expanding node A. So from node A, there are three neighbors actually, S, B and D. S we will ignore because we are already expanded. Then we have D and B. So when we are considering B, then from G of n will be from S to A it is 3 and A to B it is 4. So it will be 7. So G of n will be 7 and h of n it is given 5.8. So 7 plus 5.8, that is 12.8. Then if you are expanding D, then the starting node is actually from starting node to A it is 3, then A to D it is 5. So 5 plus 3, that is 8. So 8 plus then h of n it is given, that is 9.2. So it will be 17.2. So then when we are comparing B and D, this is the lowest value. So we are expanding B. Then D has, you can see A is one neighbor, C is another neighbor, E is the another neighbor. A is already expanded. So we are expanding E and C. So when we are considering C, then the G of n will be first S to A it is 3, A to B it is 4. So now it is 7. Then B to C it is 4. So it will be 11. So 11 plus from C to H of C will be 3.4. So it will be 14.4. 11 plus 3.4, that is 14.4. Then we are considering F. F we are considering starting point to starting point to A it is 3. 3 to A to B it is 4. Now it is 7. Then B to E. B to E it is 7 plus 5, that is 12. So 12 plus and H of E it is given, that is 7.1. So it will be 19.1. Now we can see that we actually, the second iteration what we have done is when we have expanded AS, we have two nodes A and B. And when we are comparing these two, A was low, was less. But now what is the situation? Here you can see this 13.2 is less than these two conditions. So what we will do? we will now try to expand this one because these two values are above this 13.2. So now we are stopping that path and we are coming back. So here you can see from D there are three neighbors. One is S, then A, then E. So we already expanded S. So now we will go for A. A means here the G of n will be S to D, that is 4. Then D to A it is 5. So that is 9. So 9 is G of n and H of n is given along with D, that is 9.2. So that is 9.2 plus 9, that is actually 18.2. So this is actually 18.2. Then you can see that here from D to E, then if we are expanding E, this will be S to D is 4, then D to E is 2. So it is 6. So in the E, we have 6 plus, and it is given 7.1 is the heuristics of E. So it will be 7, it will be 6 plus 7.2, that is 13 point, uh, sorry, 7.1. So it will be 13.1. So it is 13.1. So compare these two, then this will be lower. Then we are expanding E. E has two neighbors, B and E. We are not considering D. Then we have to again find. And if we are taking B, then we will see G of n will be from start node. S to D it is 4. Then 4 to E it is 2. Now it is 6. Then 6 to B it is 5. Then 6 plus 5, 11. So it is 11. 11 plus, then along with B it is given 5.8. So now it will be 16.8. And then here you can see if you are expanding in F. F then starting out S to D it is 4, 4 to E it is 2, now it is 6, 6 plus 4, E to F that is 4, 6 plus 4, 4, 10. So 10 plus, and along with the F it is given H of n, that is 3.5, so it will be 13.5. So if we are comparing these two, and here 13.5 is less, so we will select 13.5. Then we are considering the goal state to G. Now it will be G of n will be S to D it is 4, 4 to E that is D to E that is 2, 2 plus 4, 6. Then from E to F it is 6 plus 4, 10. Then 10 F to G that is 3.5, that is 13.5. So 13.5 plus G H of n will be 0. So that will be 13.5. So that will be selected. So the path will be S, D, E, F, G. Now we will see the properties of A-star algorithm, and here in this case A-star algorithm is a complete search algorithm, which means it is guaranteed to find a solution if one exists. Whether A-star find the optimal solution depends on the heuristic function used. The most important property required for optimality is admissibility. Admissibility means the heuristic, we know that heuristic is said to be admissible if it never overestimates the actual minimum cost required to reach the goal state from the node. So this mathematically we can express it as h of n is less than or equal to h star of n, where h of n is the estimated cost from node n to the goal and h star of n is the actual minimum cost from node n to the goal. Here, because the heuristics is always optimistic, then A-star search using an admissible heuristic is guaranteed to find the cost optimal path to the goal. So there are two versions of A-star search actually, tree search and graph search is there. So tree search is optimal if heuristics is admissible, and admissible heuristics never overestimates. That means the true minimum cost to reach the goal. Then graph search algorithm, that means graph search A star, graph search version of A star is optimal only if the heuristic is consistent. So that means this is stronger than the admissibility and is required because graph search avoids revisiting nodes. So here the heuristic h of n is actually consistent. So for the if every node n and the successor is n dash, then we know that g of n is caused from start node to that n, and then c of NAC, N dash, NAN dash. So that is a cost of action from A from N to N dash. Then we know that here G star of N is equal to G of N plus C of NA N dash, and here we already know that F of N dash will be G of N dash plus H of N, and that we can equate here with the G of N and C N A N A N dash, and here we can conclude that H of N which is greater than or equal to G of N plus H of N. And here the f value never decreases along with the path, and this guarantees that once node is expanded, its graph search, the breadth search to it has been found. Hence the A-star search algorithm is optimal with a consistent heuristic. And another property is actually it is complete. So meaning it will be always find a solution if one exists. And the time complexity of A-star depends on the quality of the heuristics. And in worst case, number of nodes expanded is exponential in the depth of the solution. That means big O of b to the power b, where b is the branching factor and b is the depth of the optimal solution. And the space complexity, S star stores all generated nodes in the memory. So hence the space required also grows exponentially. It will be b to the power or big O of b to the power b actually. Then we will see the algorithm of A-star algorithm. So step 1 is place the start node in open list, and if the open list is empty, then failure and also stop. There will be no solution. And the step 3 will be select the node A from the open list and have a minimum evaluation function, that is f of n is equal to g of n plus h of n. If n is the goal node, then return success and stop. Expand node n and generate all the successor nodes. Move n from the open list to the closed list. So if n is not in open or closed, we have to compute g of n dash, f of n dash, h of n dash, and insert n dash into the open list. N dash is already open or closed, and compare the new path cost with the existing one. If the new g of n dash is smaller, then update g of n dash and f of n dash. That means it's peak to reflect the lowest path. So now next step we go back to step 2 and repeat until a solution is found. And open list means nodes to be explored, and closed list means nodes already expanded, and node selection is always based on minimum f of n. Thank you.